Hello, my name is Lukas Eichmeier, and in this part of low temperature solar thermal power systems, I will give you some guidelines or some help of how to calculate solar power systems. We are going to base our calculation guidelines on the Thermosyphon system. I've already explained what a Thermosyphon system is in the previous video, but I'm going to repeat it quickly. It's a very simple and efficient way of using a flat plate solar collector, or also a vacuum tube collector, coupled to a hot water storage tank in order to produce hot water for domestic use. It is, as I said, simple, effective, and also very cheap. There is no electricity needed, as the water circulates solely on the buoyancy effect of water. The disadvantages are only that you cannot place it in regions with frost. The hot water tank needs to be placed above the collector, so outside of the house. Additionally, some people say it's not very aesthetic to have these kind of systems on top of the houses. In order to calculate these kind of systems, we need to apply a so-called heat balance, or need to apply a heat balance equation. In order to do so, we usually need to define the boundaries in which we're going to apply the heat balance. Here in this slide you can see the control volume CV, which defines the boundaries of our system, drawn in the dashed dot green line. If we now look at the energy which is stored within, or if we look at the rate of energy stored within the system, Q stored with a dot, equals to mCp times dt over dt, which needs to be equal to the usable heat which we get out of the solar collector. For a system where the usable heat, the usable power out of the collector is not a function of the time, we can replace the differential of dt over dt by increments. So we can easily calculate the stored heat, or the rate of stored heat, as a function of the temperature and the time. If now the stored heat, or if the usable heat is now a function of the time, we actually need to solve the differential equation differently. If we look at the equations on the left, we can see that we separate in the second line the two variables. We move the dt, the time, from the left side to the right side, and we add integral symbols in the third line. In the fourth line you can see that the mass of the stored heat transfer fluid, or the stored storage medium, which in our case is mostly water, and the Cp, its specific heat capacity, do not actually depend on the temperature. We can move it in front of the integral and solve the integral directly. If you go through all these steps, you end up that you can see that the change of stored heat in the system, mCp times the temperature difference, equals the integral of the usable power times dt. If you now look at the flat plate collector only, and not the whole system, so we're drawing the control volume, the boundaries, this time only around the flat plate collector, we can write a different heat balance. We can say that m dot, which is the mass flow through the collector, times Cp times the temperature difference between inlet and outlet, needs to be equal to the usable power, which is, as we have shown before, the difference between the solar input and the losses. With this equation we can easily calculate the outlet temperature of the flat plate collector. In conclusion, we can say that by using a very simple heat balance, or heat balance equations, we already have a very useful and powerful tool to calculate solar power collectors. It is important also to point out that the usable heat which we get out of a solar collector is basically, or simply, the difference between the solar heat input minus the heat losses. What I want to stress very much is that in order to calculate a solar collector, you need to be aware where to draw your boundaries, where you're going to have your control volumes, and you always want to start with a very simple system. And once you have established a very simple system, you're going to add complexity. Thank you very much. This was low temperature solar thermal power systems with simple guidelines and help for the calculation of solar collectors.